Most of the functions we have dealt with so far have been described by an equation of the form like something like y equals f of x. In other words, you can express y solely as a function of x. Expresses y explicitly in terms of the variable x. And we've learned a bunch of rules for how to find the derivatives of functions defined that way, where y can nicely get isolated, like in this case right here. But another situation can easily occur where we encounter equations such as this one right here. This is, again, the formulam of Descartes. We just learned about Descartes. If we had an equation of the form x cubed plus y cubed is equal to 9x times y, in that case, it's very hard to get y by itself in that equation. In this case, over here, we have y squared equals x. That is, of course, a parabola, except it opens to the right. And this actually, in getting y by itself, in this case, there are two solutions. Y would equal either the positive square root of x or the negative square root of x. And indeed, those two equations are described by this curve. This is the positive square root of x. So maybe I'll call this one f of x equals root x. But there's also this negative root x down here. And maybe I'll call this one g of x. This is equal to negative square root of x. All right? So in this case, this does not describe a function. The equation does not, well, it doesn't describe one function. There are actually two different functions, which is the top half of the parabola here and the bottom half of the parabola here, that satisfy this equation. Notice if you plug g of x into this equation, this implicit equation, the equation is satisfied. It is indeed the case that if I square this, the negative deletes, it becomes positive, and I have the square root of x squared, and that is the same thing as x. So both g of x and f of x satisfy this implicit equation. So it'd be nice for us to find some sort of general equation for y prime. So let me write this down. We want to be able to find y prime in the implicit case. In other words, given an implicit equation, which is usually like a curve in the Cartesian plane, we want to be able to find some sort of derivative that depends on the function. So let me write that down. It will likely depend on y. In other words, it depends on which curve is being discussed in that particular equation. We will be able to find y prime, but we won't necessarily know if it's talking about this curve, f of x root x, or this curve, g of x equals negative root x. But y prime, what we will find out, is often involves the curve y. So in other words, baked into the equation for y prime, we'll have the variable, the dependent variable y. In other words, y prime itself will depend on two variables, the dependent variable and the independent variable x. Whereas the prior y prime, or f prime of x, only depended on the independent variable x. So all of a sudden we are dealing with, implicitly, we are dealing with two variable functions, but don't get too intimidated by this. Our applications won't get too heavy in this class. When you get to multivariable class, it will get quite insane. But notice in this case as well, this curve is definitely not a function. This is not the graph of a function. Why? Because it disastrously fails the vertical line test. I don't know if you remember that from Algebra 1/Algebra 2. The vertical line test right here says that this can't be a function because it crosses this vertical line 3 times. So here, here, oh my gosh, what am I hitting here? This is what I want. Here, here, and here. Oh my gosh, I keep hitting the camera button. That's hilarious. I don't want to do that. Like this vertical line hits here, here, and here. So this curve does not describe only one function. For instance, I cannot get y by itself and have that be a unique function. Indeed, this curve can be sort of it's sort of the union of a few functions. For instance, if I were to just trace this part, so far it's still a function, and then I get up here, but I can't loop back on myself, so I better stop right here. Maybe I'll call this function f of x. So that function satisfies this curve. If I were to plug in f of x into this equation, it would be a true statement. What this curve says is x cubed plus f of x cubed is equal to, for sure, 9 times x times f of x. All right. Notice all I did was I plugged f of x in for y, for this red curve in particular. But notice that if I were to keep going along this curve, I would loop back over myself and I would stop passing the vertical line test, so I have to stop here. But then we can just talk about a new function. Maybe a new function satisfies this part. Also, we want it to be differentiable. In other words, I want it to be continuous and smooth. That's what differentiable means. For what I'm really trying to say there is, if I were to do this curve, this green curve, I don't know if you can see that, but that's not a differentiable function because it's not continuous. So I don't want to talk about that curve. So let me go over that curve. This green curve, I don't want to talk about here. I want it to be a differentiable function. In other words, I want y prime to make sense. So we eliminate curves like this. And curves, I guess, are implicitly, no pun intended, continuous set of points. So this green, quote-unquote, curve does not count. Pretend that I actually drew it as if it was a function. But so the green does not count because it's not differentiable as it's not continuous. But the red curve certainly does count. This red curve, that's f of x. And then I started drawing this yellow curve. Maybe this guy. This yellow curve counts. Notice I did not lift my pen. So this yellow curve would count. So it's a differentiable function. Maybe I'll call that one g of x. And indeed, x cubed plus g of x cubed is equal to 9 times x times g of x. Okay. But of course, there's this other piece down here, and I can maybe do this. We'll do pink, just for fun. There's this curve that comes down here. And indeed, with this curve, notice that that is smooth, and it is a function. So that also satisfies this equation. So I'll do h of x down here. All three of these different functions satisfy the implicit equation plus h of x cubed is equal to 9x times h of x. So, and if I wanted to find y prime based on this original equation, it technically would depend. Like, for instance, if I wanted to find the slope of the curve at, I don't know, 2 right here, or I don't know, whatever this value is, a. The problem with that is that technically depends on if I'm the red curve, f of x, the yellow curve, g of x, or the pink curve down here, h of x. Notice that the slope, just seeing y prime by itself, I don't know which curve I'm on. So hopefully if I solve this equation for y prime, simply what we're about to do is take the derivative with respect to x on both sides of this guy. Hopefully inside that equation for y prime, it'll tell me what curve I'm on. In other words, hopefully y itself shows up in the equation for y prime. So, so there are three candidates for y prime, or excuse me, for y. That's going to be g, f, or h. And if I want to find y prime, I don't know if I'm finding g prime of x, f prime of x, or h prime of x. But here's the thing. I'll go ahead and hop right into sort of executing this example. What I want to do is start with the equation like this. Take the derivative on both sides, okay? So this is an equation that holds for all x's. I just don't know which y I'm talking about, but what I'm going to do is take the derivative with respect to x on both sides. And please remember, this is the trickiest part of implicit differentiation. Really not that tricky. But y is a dependent variable. In other words, y is a function of x. So what that very literally means is when we take the derivative of this part right here, we do have to multiply, because of the chain rule, by y prime. Okay, so, and same thing here. When you take the derivative of this thing, we have to abide by the chain rule. This really isn't the chain rule, but rather product rule. So let me take the derivative on both sides with respect to x. I'm getting a little bit crowded and sloppy here, but you'll get the idea. So taking the derivative on both sides with respect to x, the derivative of x cubed with respect to x, that's 3x squared. That's something we've seen a million times. Now, the thing is, this y is a function. So really I have a function y inside of another function right here. Here, let me be a little bit more mathematically clear. This is the derivative of the function y cubed. And same thing here. Taking the derivative on this side, I'm going to have 9 times the derivative with respect to x of x times the function y. What I'm trying to say here is I have this part, 3x squared, and then I have to take the derivative of this with respect to x. I'm taking the derivative of y with respect to x. What that means is I have to abide by the chain rule. Take the derivative of the outside function. The outside function here is something cubed, right? So taking that guy's derivative is going to be 3 times that something squared, but then I have to multiply by the derivative of that inside something. So the inside function here is y, so I have to multiply it by y prime. On the other side here, 9, I would have 9, and then following the product rule on this side, I would take the derivative of the first with respect to x, that's 1, times the second, that's y, okay? And then I add to it the first function times the derivative of the second function, but I don't want to just put 1 down because y is a dependent variable. It depends on x. So the derivative of y with respect to x is also known as y prime. And say I want to figure out what y prime is by itself, well, I just have to do a little bit of algebra. What that means is I have 3x squared plus 3y squared times y prime is equal to 9y plus 9x times y prime. And it looks like 3's can cancel everywhere. So what I have is x squared plus y squared times y prime is equal to 3y plus 3x times y prime. And of course, doing a little bit of algebra, that shows that y prime must be the same as, it looks like I got x squared minus 3y divided by 3x minus y squared. And then going back to our equation, or going back to the 3 possibilities for the function that we want, this is where this is really kind of slick. So we found that y prime, the derivative of y, is equal to x squared minus 3y divided by 3x minus y squared. But here's the thing, like I was expressing at the beginning, I don't know if I'm talking about g, f, and h, but what's so cool about this formula is that inside the formula for the derivative itself is y. So if I wanted the slope down here, then when I plug in for h, or excuse me, if I wanted the slope of h, what I plug in for x is simply a, and then what I plug in for y is h of x. If I want the slope down here, then all I have to do is use this curve h of x to plug into these y parts, and I will receive this curve, the slope of this curve at the bottom here. If I want the slope of the curve right here, because that's also a possibility, in other words, the slope of the f of x, that part of this implicit curve, then I would plug f of x into this y part. this f of x would plug into this y part, and the x part would just be the same a. So again, what I'm kind of doing here is this. There's three possible slopes. Why is this not working? Hello? Maybe it's this? Sorry, my pen's not working for some reason. Let me try this. I wonder why that's happening. Okay, that one's working. Why isn't this? Okay, all of a sudden it's working. All right, here we go. So what I was trying to say is there are three possible slopes. Could be, let me go with blue, orange actually, this one, or this one looks like it's not quite as steep, or this one. And to find whichever one you want, all you have to do is plug the corresponding function value into your formula for the slope to get that slope. All right, so it depends on, you might have alternate goals here. All right, so in a similar fashion, just to get a little bit more practice, I'm going to look at these guys over here. So we have two possibilities for this one. And let's say, to get a little bit more, this is a little bit more of a practical example. What I want is y prime from this equation. So what I do is, like we did in the last example, I'm going to take the derivative with respect to x of both sides of this equation. That's a little bit of an abusive notation, but that's all right. So this implies 2y, again, on the left-hand side, y is a function of x. So I better multiply this by y prime. I just used the chain rule. And this is equal to 1. The derivative of x with respect to x is 1. In getting y prime by itself, I would have that y prime is equal to 1 divided by 2y. Okay, so now say that I have x equals 4 right here. Then this point would be 2 comma 4. Or excuse me, 4 comma 2. This would be 4 comma 2. And that would be a point on my curve f of x. And I also have the point down here. This would be 4 comma negative 2. That would be a point on the curve g of x. If I wanted a machine that would tell me I guess I can just answer either one of these questions. If you know the point that you're curious about, then you also know the slope there. So this would be like the slope of a tangent line at a particular point. Say I wanted this one, m1, then I would simply plug in this y value, this 2y value. So this would be into my y prime equation. So this is a machine that tells me the slope at any y value. So this would be 1 over 2 times 2, where this 2 is this 2. And of course, that would be 1/4. But what would I do for the slope down here? That would be 1 over 2 times, not 2 this time, but it would be negative 2. And that's going to give me a negative 1/4. And looking at the picture, that would make sense. But say, rather, I wanted a machine that told me the slope of this curve at any point, then I would simply grab, I wanted a machine that would tell me the slope of this curve at any point. Then I would simply plug g of x into my slope machine for y. If I wanted a machine that told me the slope of this thing at any point, then I would grab f of x and plug that into my slope machine for y. Okay, one more sort of example. This is going to be kind of like half a theory video and half a example video. This, of course, can be illustrated. A circle with radius 5 can be broken up into two different differentiable functions. Let me grab one of them. One of them is this curve up here, f of x maybe. And this would be, of course, f of x is equal to the positive square root of 25 minus x squared, simply by finding or solving for y squared here, or solving for y here. Y would equal plus or minus 25 minus x squared. So there are two curves that satisfy this equation. The positive and the negative root 25 minus x squared. Those of you guys that are staring at this video, hopefully you understand that this curve is the other curve. That negative square root of 25 minus x squared, let's call this some g of x. Okay, and say I wanted to find the tangent line of this curve, or this point right here. So I'm going to use the g of x, and let's just call this point. This would be, let's go 3, negative 4. First of all, you should confirm with me that if you plug that into this curve, it indeed satisfies this equation. Okay, so 3 squared, that's 9, plus negative 4 squared, negatives cancel, that's 16, 9 plus 16, 25, sweet. So I'm not too crazy on choosing this point. And I want to find the slope of this tangent line right here. All I would have to do, grab my curve, my implicit equation, and take the derivative on both sides with respect to x. So the derivative of x squared with respect to x, I'll do like this. Taking the derivative with respect to x, I get 2x plus 2y times y prime. Why? Because y is a dependent variable depending on x. If we're taking the derivative of y with respect to x, you have to use the chain rule. This y, this function y, is inside this other function something squared. So the derivative of something squared is 2 times that something, but then I have to take the derivative of that something because of the chain rule. And then, of course, the derivative of a constant 25 is 0. Solving for y prime, what I get is that negative x over y is the equation of my slope. This is a slope machine. Notice it depends on y. So y could either be the f of x that we were just talking about or the g of x. So that y could either be f of x or g of x. And in this case, it's going to be the g of x, but I don't really need to concern myself about the function because I only, in this case, need the tangent line or the slope of the tangent line at a particular point. So to find this slope right here, I simply plug the right thing into this equation. And that's going to be y is in the denominator, that's negative 4, x, so y is in the denominator, negative 4, x in the numerator, here's x, here's y, 3, so that's going to be positive 3/4. Now, you should always do kind of like, if you have the luxury of a picture, you should do a fact check or just a sensibility check. This is a positive slope, and looking at the picture, yeah, it makes sense. That's a positive slope. For instance, if you got like negative 10 or something, you'd be like, well, that's clearly messed up. The slope here is, the tangent line here is definitely doesn't have a positive slope. All right. So that was a good sort of summary of what implicit differentiation is, but I wanted to show you how this can actually be used to find derivatives of inverse functions. So I have our PDF of derivative rules up right here. Everything underlined in blue is what we have proven already. So we have all our rules for differentiation right here, the sum rule, the product rule, the quotient rule. We have the power rule for the integers. We have the famous chain rule, which is super helpful. We used the chain rule to prove the power rule for the rationals. We introduced ourselves to the exponential function and its inverse. And then we have random exponential functions, a to the x, log base a of x. And then using those exponential functions, we proved the power rule for the real numbers. And we also have famous trigonometric derivatives. We really used the derivative definition for these. In other words, we used the fact that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. If there was something for you guys to remember in this class, it honestly would be that definition and the equivalent definition. But once we had the chain rule, we were actually able to prove, or once we had the chain rule and the product rule and the quotient rule, then a lot of these were easily proven once you had proven the first two, because the tangent function is simply the quotient of the sine and cosine function. The cosecant function is simply the reciprocal of sine, which means you can use the quotient rule. The secant function is the reciprocal of cosine, which means you could use the quotient rule. And the cotangent function is the quotient of cosine and sine. Again, you can use the quotient rule. So these came via the limit definition. All of these came because we had these two and the quotient rule. But what if I want to talk about not the multiplicative inverse of the sine and the multiplicative inverse of cosine, but what about the function inverse of sine and cosine? Indeed, with this implicit differentiation, you can actually quite quickly solve for the derivative of sine inverse, cosine inverse, and tangent inverse. And at its core, it's really not implicit differentiation we're using to prove these, which is what we're about to do. It's really the chain rule. But let's see one of them. I'll start with tangent, and maybe I'll leave the others to you guys. Suppose that f is a function defined from the real numbers to the open interval negative pi halves to pi halves. And it's defined by f of x is equal to the arctangent of x. I want to prove that f prime of x is equal to 1 over 1 plus x squared. Okay, so this is for sure one of the derivatives that you need to just know. So we'll use it hopefully enough in this class to see it, but it is definitely one of those derivatives that you have to just know, and we're about to prove it. All right, let's do it. Proof. Let y equal f of x, which equals tangent inverse of x. Okay. Well, wait a second. By definition of inverse functions, that means that tangent of y is equal to x. Okay, so you might ask why. This is like definition of the inverse function. So I'll write because, and in like sort of a thought bubble, I'll go with a is equal to f of b if and only if f inverse of a is equal to b. Okay. So this function, what it looks like is this function kind of hops to the other side of the equal sign, but becomes the inverse function. These aren't the same function, of course. And another thing you can recognize that I like to point this out. If both of these are true simultaneously, that means that b has another name. In particular, the other name for b itself is f inverse of a. So how does that change this part right here? That means I can rewrite this as a is the same thing as f of f inverse of a. Indeed, that's kind of like a defining property of inverse functions. But also, both of these are simultaneously true, which means that a has a different name, and that's f of b. This is a review. In other words, f inverse of f of b must be b. All right. So that's all I've used so far. But now I can sort of use implicit differentiation. And I'll take the derivative on both sides. I know the derivative of the tangent, and the crucial thing here is I have to remember that y itself is a dependent variable. It is a function, and it literally says this right here. But y is a function, so what that means is I need to multiply by the derivative of that function. But taking the derivative of the outside function here, the outside function being tangent, That's secant squared of y, so of the inside function, but then I have to multiply by the derivative of that inside function. And guess what? This is y prime. So that is what we're going to end up solving for. And taking the derivative of x with respect to x, that's going to be 1. So indeed, y prime is equal to 1 divided by secant squared of y. So we're done, right? Oh, shoot, what the heck? Apparently x is in there. So in order to figure that out, how I can see, notice that I'm not done because I have secant squared of y here and I have 1 plus x squared here, which means that I have more work to do somehow. And the key insight, this is clever. This, associated with this sentence, is a triangle. So here's my thought bubble. Notice that I have tangent of y. The thing that goes on the inside of the tangent function is the angle of a right triangle. Okay? In other words, what I should do is label one of these angles by y. Okay? But I also happen to know that the tangent of y, tangent is the opposite over adjacent side here. I happen to know that the tangent of y is equal to x. In other words, I have that opposite over adjacent is equal to x. But due to, I guess, similar triangle theory, I simply have to choose one ratio that works. So why don't I just make my job easy and say that let's declare that this opposite side is x and declare that this adjacent side is 1, because then in that case, it is indeed the case that tangent of y is opposite over adjacent. Oh, that's x over 1. In other words, that is x. Okay, so this triangle is what should hop into my head when I wrote this sentence down. The thing that goes on the inside of the trig function is an angle, has to be, and this is simply a ratio. The x is simply a ratio according to what the tangent function is by definition. But now we have the Pythagorean theorem to figure out what this object is. We can solve for this object, the hypotenuse. Indeed, 1 squared plus x squared is equal to h squared, which tells us that h is the square root of 1 plus x squared. Now, secant, coming back over here, secant is the reciprocal of cosine, which means that the reciprocal of secant is also cosine. In other words, this is the same thing as the cosine of y squared. And so I'll justify that. That's because 1 over secant is equal to cosine. In particular, secant is the same thing as 1 over cosine. Those are both the same, as long as cosine's not 0. But shoot, now I just need the cosine of y. Okay, look at the triangle. We know what the cosine is. The cosine is adjacent over a hypotenuse. So the cosine of y is simply 1 divided by 1 plus x squared. The square root of 1 plus x squared. Yikes. Oh, shoot. That's where we have it. Through squaring things, the square root and the square cancel out. And therefore, y prime, which is the same thing as f prime of x, must be the same thing as 1 over 1 plus x squared. Congratulations, ladies and gents. Going back to our derivative rules, this one's proven. We now can use this at our own will. These two, I'm going to let you guys do it for homework, just to keep this video sort of shorter. The process is the same. Just make sure you adjust accordingly for sine and cosine. In the next video, we will assume that we have these two. There are, of course, others like secant inverse and cotangent inverse, and those are really a lot grosser, and you have to be a lot more careful with domain restrictions. So this is horrible. Maybe I'll talk about those in the what do you call it? The Actually, that's a great idea. I'll talk about those in the bonus video. But I won't test you on those, I don't think, just because I think they're so horrendously nasty. Even though they sometimes, the world doesn't let you decide what machines are most useful. So that's why I'll address it in the bonus video. Okay, so we have this at our hands, and I wanted to point out that this could have also been proven with the same implicit differentiation sort of argument. And this guy down here, the quotient rule for Q, could have been proven with an implicit differentiation argument. But let's see like a quick application here. If I wanted to say, what is, G is equal to 3x times the inverse tangent of e to the negative 1/2 x. That's a good one. Find G prime. Well, we have to use the product rule. This is the same thing as the derivative with respect to x of 3x times, don't touch the second derivative, the second function, tangent inverse of e to the negative 1/2 x, plus the first function, leave it be, times the derivative of that second function. We now know the derivative of that second function, tangent inverse of e to the negative 1/2 x. Okay, this derivative right here is quite easy. That's 3 times tangent inverse of e to the negative 1/2 x plus 3x. And now I have to take the derivative of this function. Notice I have the chain rule or the composition of 3 functions, which means I have to use the chain rule for this guy right here. And I go outside in. So the first function I'm going to have to take the derivative of is the tangent inverse function of some blue blob here. Okay, so this is in dark blue. So what I'm going to do is use this new derivative function, or this new derivative I just discovered. The derivative of tangent inverse is going to be 1/1 plus whatever that blue thing is squared. And then I have to, by the chain rule, multiply by the derivative of that blue thing. Okay, that's the chain rule at its core. Okay, so fixing things up here, this is the same thing as 3 times the arctangent, or the inverse tangent of e to the negative 1/2 x plus 3x times 1/1 plus, but what am I going to plug in right here? That's going to be e to the negative 1/2 x. That is the blue thing. But then I have to multiply by the derivative with respect to x of e to the negative 1/2 x. All right. Simplifying this a little bit more, we will notice that we have 3 times tangent inverse of e to the negative 1/2 x plus, I'll put 3x in the numerator, 3x divided by 1 plus, and notice I have some exponent rules here. These two exponents come together via multiplication, leaving me with e to the negative x. That's kind of nice. Times, I want to multiply by the derivative of this function. But notice this is also the chain rule. I have an outside function that's e to the power of, I'll go orange blob. Okay. So I have to first take the derivative of that outside function, but the derivative of e to the orange something is just e to the orange something. But then the chain rule dictates I have to then multiply by the derivative of that orange something. Okay. So rewriting, I have 3 times tangent inverse of e to the negative 1/2 x plus 3x divided by 1 plus e to the negative x times e to the orange thing, which is negative 1/2 x, times the derivative of that orange thing. I'll just go ahead and I won't do any more details here. That's clearly negative 1/2. The derivative of this orange thing right here is simply a number times the variable x. and leaving me with just -1/2. Okay, let's see. Maybe something can simplify right here. I am actually seeing, yes, there's some simplifications that could happen. I'm going to say this is 3 times tangent inverse of e to the -1/2 x minus 1/2. And I'm going to multiply the top and bottom of this guy by e to the x. I'll multiply by 1. Then I can distribute that. So my numerator, I have 3x times e to the x. But in the denominator, what happens is I have e to the x plus 1. And then I still have times e to the -1/2 x. This -1/2 was taken out front. So this is going to leave me with 3 times arctangent of e to the -1/2 x minus 1/2. And it looks like I got, or I'll do 3/2, minus 3/2 x times e to the, so I have e to the x times e to the -1/2 x, -1/2 x, and that's going to simplify to e to the 1/2 x. Know your exponent rules. All divided by e to the x plus 1, and this will give me a final answer. Best way to do this. 3/2 times 2 e to the x plus 1 arctangent e to the -1/2 x minus x e to the 1/2 x. That x should not look like it's in the denominator. 1/2 x. This one too, I'm being a little bit sketchy. That should 1/2 times x, not 1/2x. All divided by e to the x plus 1. There you go. So that was a quick differentiation application of this new derivative that we found. We just proved it right here. It's something we got to know, something we got to get used to. In fact, this process that we did can be generalized in a big theorem, last thing I'll say here, called the inverse function theorem. If f has an interval I as domain and f prime exists and is never 0 on I, then f inverse is differentiable on its domain, which is the range of f. In particular, the value of f inverse prime at a point B in the domain of f inverse is the reciprocal of the value of f prime at the point A equals f inverse of B. In other words, this holds. This is called the inverse function theorem, the simplest version of the inverse function theorem. This gets quite complicated when you get to multivariable calculus. But the theorem, in order to prove part of this, we actually do not have the tool. This blue underlined part, we don't know how to prove yet. Not quite. We need something called the mean value theorem in order to prove that. So I'm going to hold off on a few weeks to prove this, but don't worry, I'm not abandoning the mathematical process. That process being everything in math is proven, not just handed to you. I will spend some time in a future bonus video proving the inverse function theorem once we have proven the mean value theorem, whatever the heck that is. But this part right here, I actually argue, is something we can prove right now. And also I'm going to draw a picture before this part, before I kind of dive into this. So I'm going to assume that f is a function where that's differentiable on the entire interval, which means it's smooth, and it's never 0, which means that I have to draw a function that is never flat and is smooth. So let me maybe try something like this. I'll do, just so we can kind of see what's happening right here, what this function says. I'll kind of decode the crazy mathematics. Okay, so let's talk about this interval. Maybe. So here's this interval. And let's say my function looks something like this. So again, my restrictions are my function has to be smooth and it can never be flat, which means that it's either strictly going up like this, or I could have drawn it strictly going down. Notice that the slope is never 0. That's what this part means. F prime of x exists and is never 0. So yeah, we have a nice slope here and it's never 0. And we also have that it's smooth. Yeah, and it's continuous. Okay, so here's my function f of x defined on the interval I. So here's an interval I, and here's f of x. And say I wanted to talk about, I don't know, maybe a particular slope. So let's talk about, let me choose a nice color. Let's do this point right here. I'll do A, comma B. So this point would be, I'm making sure this is gonna make sense in terms of the theorem. And I also want to talk about what this is sort of mapped to, what set this is mapped to. So here's the interval that is the domain of f. Okay, so that's the domain of f. What that means is the range of f is going to be this interval. So here's the domain of f, or excuse me, the range of f, which is that interval. And then b would be some value in here. So we got a comma b. This would be a, this would be b. And I want to talk about the slope of this guy. So this picture is going to get a little bit crowded. Let me move the a comma b up here. Erase this. This guy. So let's say I want to talk about this guy's slope, and I'll try my best. I already used orange. I've been using orange. So if I wanted to draw this, I want to be as accurate as possible. So let's say rise looks like this, and the run maybe looks like this. I want to pretty much draw this exact same picture, and we want to ask what this slope is going to look like in terms of the inverse function. So something you should remember, so I is equal to the domain of f, and this green is equal to the image of f, or the range of f. And remember, with inverse functions, the range of f becomes the domain of the inverse function. In other words, I'm going to imagine that I have a nice line here, y equals x. This is, by the way, the x-axis. Y-axis, y equals x. And I'm going to flip this picture over this imaginary axis right here. And what is that going to look like? Well, this green map right here is going to flip to the green, or excuse me, the x-axis right here. And that's actually going to be the domain of my inverse function. Okay, so this is the domain of my inverse function. So I can write that down here. That's the domain of f inverse. Those are the elements that f inverse takes in. And then this thing right here, this is going to sort of flip and map up here, and that's going to be the range of my inverse function. So let me see what that's going to look like. It should be like same measurement. So this is about where it starts. Maybe right here. Okay, here's the range of my inverse function. Then you might think, what does the inverse function actually look like? Well, we can sort of draw it. we're wondering about, so f prime of a here. Let me finish drawing. What is this inverse function going to look like? All I have to do is something like this. And it looks like our inverse function. So again, I'm about to map the inverse function. It's going to look something like this. Yep. And here's my original function. I drew the tangent line. Okay. So this yellow, or f prime of a, I bulked up my, here we go. F prime of a is equal to blue over red. So that's the blue, the rise over the red, the run. I want to figure out what f inverse prime of b is. Okay, so notice b, where does b get mapped to? So here's b on the x-axis. Here's a on the y-axis. So f inverse takes in b and outputs a. Oops, that should be a. What I'm wondering is what this, if I were to take this tangent line, and you can kind of see it intuitively. That's what this theorem is all about, by the way. Here's the tangent line. Here's my tangent line for f inverse. So again, f inverse of a is the slope of this. Let me do this. Point to this. The slope of that line right here. Notice this. In order for this to make sense, what do you think the derivative, literally what this is all about? If I were to ask you what f inverse prime, the derivative of f inverse at b is, well, that's going to be the same thing. Based on the picture, looks like I have a rise of red. So b, let me use the right color, just so this picture makes sense. The rise of red divided by the run of blue. Oh, shoot, that's kind of nice because that is the same thing as the reciprocal of blue over red. And of course, that is the same thing as 1 over f prime of a. So to summarize, actually, I think I'm going to use this as my sort of proof. This is not an official proof, but this is almost the better way to sort of think about mathematics. Draw it and convince yourself of it first. So the facts that we have right now are that f inverse prime, I'll use blue, light blue, go back to light blue. So here are the facts. F inverse prime of b is equal to 1 over f prime of a. But at the same time, we know that f of a is equal to b, which is synonymous since we have an invertible function. A is equal to f inverse of b. And indeed, the typical equation, what you do is you take this and plug it in right here. So in other words, my sort of proof by picture, which is not a valid proof. That's exactly what Balzano went crazy about. He said, yeah, no, you can't do that. F inverse prime of B is equal to 1 over F prime of F inverse of B. So that is at least the idea for the proof of this big theorem. Something like this. And I like convincing yourself. It's important in mathematics in general to convince yourself that a theorem is true before you just hop into it and prove it. And I like the picture with the colors. It's very convincing to see what we're trying to say. So yeah, this was absolutely crucial, convincing yourself of the inverse function theorem and what that inverse derivative must be. Remember, derivative is simply the slope. So if we have the slope of the original function, blue over red, what must be the slope of the inverse function? And the process of showing this part, like actually, this part right here, you guys, it's so similar to what we did with the tangent inverse proof. I might leave it to you or something like this to actually prove.